when we run the beam through the container full of Mountain Dew, here's the container. You remember we saw the beam going through this. And you have an experiment to do with that. We have the outline of the container. We see that this outline fits just fine. And we've marked points in the beam, as you saw, so that we have a pretty good idea what the path of the beam was as it came in, as it went through, and as it came out of the Mountain Dew, which is essentially just water. The index of refraction of Mountain Dew, especially Diet Mountain Dew, I don't think differs much at all from the index of refraction of water. Now, having obtained these rays, we drew perpendicular lines here and here, lines perpendicular to the outline of the cassette case that formed our lens. Okay. Now, we made some measurements to determine some of these angles. The angle of incidence, which is the angle of the incoming ray or the transmitted ray with the normal or perpendicular to the outline of the the outline of the case, can be determined by constructing a right triangle here, and we constructed that triangle using any convenient right angle. We just went down some arbitrary distance here, made a right angle, and came across to this line, forming this right triangle. Then we took a ruler and measured this distance, and we measured this distance, finding 4.47 centimeters and 3.65 centimeters. The tangent of this angle is this opposite leg over this adjacent leg. As long as this is a right triangle, then these two legs tell us what this angle is. We simply divide this by this and take the inverse tangent on the calculator. So we divide this by this, hit the equal sign, I guess, just to be safe, and then take the inverse tangent, and we get 39 degrees. So we see that the angle of incidence here is apparently 39 degrees. Making similar measurements on a similar construction here, we obtained 2.1 centimeters for the side opposite the angle, 3.9 for the leg adjacent to the angle. And we take the inverse tangent, 2.1 over 3.9, and get 28.3 degrees. We do the same thing for this angle, and we get 25.5 degrees. Now, if we stop and think about it a minute, if we just look at the outline of the casing here, this side of the casing ought to be parallel to this side of the casing, and if this is a straight line, which it pretty much is, then wouldn't we expect these two angles to be equal? These lines, this line and this line, should be parallel, being perpendicular to parallel lines themselves. And then we have a transversal of a parallel, and these two should be equal. As I look at these lines, I think this one is actually angled out a little bit. I don't think we did a very good job of making that one perpendicular to something. And that might be because we don't have a real good tracing of this side here. Okay? In any case, we get two apparently different angles here. However, when we come up to this angle, we get 38.7 degrees using the measurements that we made, and that matches pretty well with the 39 degrees we have here, 38.7, 39, and these rays should indeed be parallel. So it's a little hard to say exactly what went wrong here, but we're off by a few degrees on some of these angles. So what we get isn't necessarily going to be really, really precise. Now, we have this law which is called Snell's law. Here's the law. It says that the sine of the incident angle over the sine of the refracted angle is equal to the ratio of the velocities of the wave or the light in the two medium. So that if V1 is the velocity in air coming in for the incident angle, and V2 is the velocity of light in the water or Mountain Dew, if there happens to be a difference, then we have this ratio. Now let's come back here a little bit. Okay. Now, we have this N2 and N1. If this is the incident angle, and we assume now we've maybe turned our orientation around, we're coming in from the air like this. And then we're refracting into the water like this. So the incident angle is theta I, the refracted angle is theta R. The speed of light in this medium, which in this case is air, is V1. And we're going to say that V1 is C over N1. Okay, this is our definition of N1 actually. Where C is the speed of light in a vacuum. So if we divide the speed of light in a vacuum by the index of refraction N1, we get the speed of light V1. So, in the medium. Speed of light in a vacuum divided by index of refraction equals velocity in the medium. For air, N1 is, I think, something like 1.0003 or something like that. It's very close to 1, so that the speed of light in air is practically the same as the speed of light in a vacuum. On the other hand, as we go into the water, we get a much lower speed of light actually. Okay? The light slows down considerably in water. The index of refraction as measured and accepted is approximately 1.33 or 1.34, about 1 1/3, very close to 1.